Hello students, today we will discuss about the definition of vector space in linear algebra. Before going to the definition, we need to learn two things, internal composition and external composition. Internal composition means take two elements from the same set and when you are applying any operation, that is nothing but internal composition. And external composition means when we are taking one scalar set and one vector set, two different sets, and when you are taking two elements from two different sets, then we are applying operation, then it is belongs to vector set, that is called external composition. Means here we are taking from the same set two elements and here we are taking two elements from two different sets. One is scalar set and one is vector set. Now we are discussing about vector space, that is take any vector space, vector set like V is any non-empty set of objects which is called vectors. Then we are taking two operations, addition and multiplication, and we are taking the scalar set also. Generally we are taking as a field set. Now we should satisfy 10 conditions, that is take two elements from vector set, then when you are adding, then same resulting element will be belongs to the same set, which is also nothing but vector addition in that is what closure property in vector addition. Now in the same way, commutative property like u plus v equal to v plus u, and associative property, take any three elements and adding in a different manner, then it will be same. Now identity property under addition, that is take any element from vector set and 0 vector from vector set, then u plus 0 bar is nothing but u, which is nothing but what identity property under addition. In the same way, inverse property under addition, that is take any element from vector set, any vector from vector set, and take minus u belongs to v, then when you are adding, then 0 vector will come. So this is inverse property. And this is what scalar multiplication. Scalar multiplication means take one field element and one vector element, then when you are multiplying c into u, which is belong to vector set, this is also called scalar multiplication. Similarly, we are taking one scalar, two vectors, then we can have the distributive property, and two scalars, one vector, then we can split it like cu plus du. Next, take two scalars, one vector, then we can multiply in any manner, that is c into du equal to cd into u, and last one is 1 into u equal to u. So here first 5 properties are related to internal composition and last 5 properties are related to external composition. So if it satisfies all the 10 properties, then we can say it is a vector space. Okay students, now examples for vector spaces R2, R3, R4. In general, Rn is also a vector space and a set of all polynomials with degree n is also a vector space. Now coming to subspace definition. Subspace means take any set H of a vector space which is a non-empty subset of V and itself it is a vector space. Means it should be a non-empty subset of V and it should satisfy all vector space conditions, like 10 conditions should be satisfied. So instead of satisfying all the 10 conditions, we have one short definition for subspace, that is take any H is a vector subspace of a vector space V which is a subset of V and it should satisfy 3 properties instead of 10 properties. So first property is 0 bar must be belongs to H, means 0 vector must be in H, and second one is it is closed under vector addition, that means first property in vector space, it is that is nothing but closure property. So it is closed under vector addition and it is closed under scalar multiplication, means sixth property in vector space. So if it satisfies all these 3 conditions, then we can say H is the subspace of V. Now let us discuss some problems. 0 bar is a subspace of V. So let us take the subspace as 0 bar. Then we need to prove it is a subspace. Previously we discussed that to prove it is a subspace, we need to satisfy 3 conditions. One is what? 0 bar belongs to H. Obviously 0 bar is in H. So first condition satisfied. And what is the vector addition? Take two elements. Here only one vector is there. So take 2 times the same vector, and when you are adding, same vector will come which is also belongs to H. So vector addition has proved. Similarly, for scalar multiplication, take any scalar and take vector, and when you are taking the product, same vector will come which is belongs to H. So it satisfied three conditions means 0 bar is a subspace of V. So by taking the polynomial set, take any polynomial which is Pn is a subspace of P means a polynomial with degree n is a subspace of set of polynomials. So what is the set of polynomial? A0 plus a1x plus a2x square and so on up to, and it is up to endless, right? This is one polynomial. This is nothing but the vector space. And Pn means it is a polynomial with degree n. So we need to write up to an x power n. Then to prove Pn is a subspace of P, what we need to prove? Three conditions. So first condition for subspace is 0 bar belongs to Pn. So 0 bar, how you can write as a polynomial with degree n? Simply 0 plus 0x plus 0x square and so on up to degree n means 0x power n, which is obviously belongs to Pn. So 0 bar belongs to Pn. Now to prove vector addition, take two vectors with degree n. So suppose I am taking u as a0, a1x and so on up to anx power n. Similarly, we can take some another vector b with the degree n. Then when we are adding, what will happen? U plus v. Take the constants at a time and x terms, then a1 plus b1 x and so on up to x power n terms means an plus bn x power n. So it is also a polynomial with degree n. So obviously it belongs to Pn. Now vector addition proved. Similarly, scalar multiplication means take any c which is a scalar and take c into u means c into u. Then multiply c a0, c a1 into x and so on up to like this. So which is also a polynomial with degree n. So it is obviously belongs to Pn. So scalar multiplication also proved. So from these three cases, what we can say? Pn is a subspace of P. So in the next video, I will discuss about the linear combination and relevant theorems. So thanks for watching.